call this meeting to order. How's everybody doing today? Yeah, okay. Well, a little bit tired. I mean, that's to be expected. So, we got a lot to cover and not a lot of time to cover it in. There's a very strong possibility I'm going to get the call today or tomorrow, so we'll see. But if it'll be during this class, that'll be a very comic situation, which will be recorded on camera, which I'm sure everybody will enjoy afterwards and make memes of. But anyway, so let's get continuing on from where we were. The things I'm planning to get through today, we're going to talk about the complexity of merge sort. We're going to talk about how to solve a recurrence equation for its time complexity, and we are going to talk about quicksort, which is our next advanced sorting algorithm. So, I ran through the rough sketch of why merge sort is n log n yesterday, or Monday. Incidentally, anytime you see LG instead of LOG, that means it's the base 2 logarithm. Logarithm, if it's, okay. Log n is base 10, right? LG n base 2. Log with some subscripted x is base x. We're going to see that today. And of course, no, we're not going to use it in this course, but the natural logarithm ln n is base e. Right? Quick logarithms review. So, let's actually, so we sort of have hopefully an intuitive sense of why this is the case, that we have this logarithm term added here. But we also have a math reason, so we're going to go through the math reason as well. So, the derivation, mathematically, of this logarithmic runtime is derived from what we call a recurrence equation. So a recurrence equation is it's a recursive equation. You may notice where we have c at n is less than or equal to the ceiling of n over 2, and you apply the c function to that. You have the floor of n minus 2, and you apply the c function to that, and then you have an n added in there. That is a recurrence equation, because the equation is defined by sub-instances of the same formula, right? So, the question then becomes, well, okay, so let's relate this to the algorithm itself, right? What we're trying to determine is the runtime complexity of merge sort. This is primarily based on the number of the number of comparison operations that merge sort performs. The number of comparisons it performs is related by this equation. You have the number of comparisons. I don't know why the textbook calls it compares. That's incorrect grammar, but it does so consistently. Little pet peeve of mine. I've corrected it in the slides wherever possible. Some of these are actually images taken from the textbook. But anyway, so the number of comparisons we perform is equal to the number of comparisons performed in the left half plus the number of comparisons performed in the right half plus the number of comparisons which are performed at the current level. The maximum number of comparisons we have to perform is, of course, n, right? We're going to get into best and worst case as we go on here. So, if you're not familiar with the sort of upper bracket, lower bracket notation, that is the mathematical symbol, those are the mathematical symbols for ceiling and floor operations, right? So, ceiling is the smallest number, smallest integer greater than or equal to x. So, of course, the ceiling of 1.5 is 2, 3.1 is 4. Ceiling means round up. Floor means round down. Capisci? Good. So, we solve this recurrence when n is a power of 2. So, d at n is equal to 2d n over 2 plus n, for n greater than or equal to 1. So, and of course, when we're trying to find a base case for the number of comparisons, if we have a singleton array, we do not need to make any comparisons, so the number of comparisons is 0 in that case, right? So, the general proof for this is a little bit messy, but we'll get into how to solve these recurrence equations. So, a recurrence relation is an equation that defines a sequence based on a rule that gives the next term of a function as a function of previous terms. A recursion tree is useful for visualizing what happens when such an equation is iterated, documenting not only the number of recursive calls, but also the amount of work done at each step. In a recursion tree, each node represents the size and cost of each subproblem. We sum the costs in each level of the tree to obtain a set of per level costs. Then we sum all of the per level costs to determine the total cost of all levels of the tree. So this is the explicit procedure laid out that we were following when we, on this slide, said, well, d at n is going to be n at the top level. We've got 2d at n over 2's here. So that's 2 times n over 2, which is n. We've got 4n over 4's at this level. 4 times n over 4 is n. N. Maximum depth of this tree is log n, so n log n. Right? With me so far? Any question? Yep. So, merge sort divides the array into 2 equal parts at each step. The second level of the recursion tree contains 2 to the power of 1 subarrays of size n over 2 to the 1. The third level has 2 to the power of 2 subarrays, each of size n over 2 to the power of 2, and you can see, etc., etc. Depending on the height you're at, you have 2 to the power of h arrays of size n over 2 to the h at maximum. In actual fact, unless the number of elements in the array is an exact power of 2, you will end up with the last level being incomplete. Once again, we are looking at our maximum runtime characteristics. So we're going to sort of slide past the idea that this final level might be incomplete. So long as the structure of the tree is still a binary tree that doesn't have any mysterious missing branches, everything will still work out. So, in general, yes, we are processing 2 to the power of h elements of size n over 2 to the power of h. So, of course, per level, each level is big O n. But how many levels are there? By construction, merge sort creates complete binary trees. So, the number of levels in a full binary tree, where the n is the number of nodes at its deepest level, is log n. Therefore, we have n items being processed, log n times, making merge sort an n log n or linear algorithm. Make sense? Good. So let's talk about how to solve recurrence equations. Consider the size of the subarrays at each iteration. If the algorithm creates equal subarrays, then every path of the recursion tree has the same height h. However, this is not necessarily the case for all algorithms. When we talk about quicksort, hopefully in not too much time, one of the advantages derived from quicksort is that we are making an intelligent decision about partitioning based on the values in the array. This allows us to obtain a better algorithm. One of the consequences of this is that you may end up with unequal partitions, right? If you end up with unequal partitions, obviously you can partition this guy way more than you can partition that guy, right? So this branch of the tree is going to be deeper. It's going to have a greater height. Does that make sense? So when we are examining things for a worst case runtime scenario, do we examine the shallowest tree depth or the deepest tree depth? Okay? We go for the deepest, right? Because that's going to be our worst case scenario, right? So to determine the tree height, we must examine the longest path. At each division, the subarray with the most items will take the longest to be subdivided down to the arrays in one item. Therefore, the longest path will always follow the largest subarrays, and this path is the height of the tree. With me so far? Good? Good. Excellent. So, to determine the height of this longest path, we formulate an equation. N is equal to k to the power of h, n over k to the power of h is equal to 1, where k is the fraction by which n is divided at each level. So the one thing about quicksort is that the partitioning is not stable, right? It can occur around pretty much any element. Sorry?
Sorry, it's not zero. Sorry about that.
Oh, that's okay. So because the partitioning is random for quicksort, essentially random because it depends on the elements, we can't derive a recurrence equation that has stable fractions, right? However, the situation we're kind of in here is, say you had an algorithm that always partitioned like, 1/3, 2/3, right? Or maybe you have an algorithm that partitions into three partitions rather than two equal ones. Like, how do you solve these equations, right? So, computing the time taken at each level and multiplying it with h will give you the order of the total complexity of the algorithm. So, in this particular example, consider t at n is equal to t at n divided by 10 plus t at 9 over 10 n, right? So we take 1/10 and we follow one path. We take 9/10 and we follow the other, right? And then, of course, we have our c at n term. Make sense? So, this equation is being divided unevenly. In this case, the left branch is getting 1/10 of the elements, and the right branch is getting 9/10 of the elements, right? The largest subarray dictates the tree height. Which one is that in this case? The right side, thank you. At the second level, the largest subarray is 9 out of 10n. At the next level, the largest subarray is 9 squared n over 10 squared n, and so on. At the maximum depth, n over 10 to the 19th power of h is equal to 1, where h is our maximum tree depth. So this is where this equation comes from, right? This equation to 1. We're looking for the height at which the array is subdivided down to one element. That's going to be a function of both n and h, but we can derive an equation for n in term we can derive an equation for h in terms of n, which is roughly speaking how big O works anyways, right? With me so far? I know this is math, but question?
What is C?
C is Sorry, is that on this slide or the previous? Right here? Oh. So C is your regular amount of time things take constant as we normally see in O, in big O notation, right? This term here is the amount of time that it takes to process the level that you're at, right? So if we go back to merge sort itself, right? Sure, at, for example, this level, we are merge sorting half of the array, right? It not only takes the amount of time to, that takes the amount of time it takes to merge sort these two, but then we also have to perform the merge on these two sorted arrays. That is going to take an amount of time which is linear on the size of this of these two together, right? That's what's encapsulated by that term that we're adding. Does that make sense? Cool. Any other questions? That was a good question. All right. So, where were we? So if we solve this equation, we yield h is equal to log 10 over 9n. Each level of the tree takes c at n. So with h levels, the total time taken is big O n log base 10 over 9n. Does that make sense? So if I gave you a recurrence equation on a test, you'd be able to find out what the time complexity of it is? No? Maybe I'll put a few on an assignment that you can have some practice. Good. Any questions about that? Okay. So, I'd like to talk, not too long now, about two different approaches to the same algorithm. The merge sort that I showed you last time in class, that's what's known as top-down merge sort. So in top-down merge sort, you're sort of always working towards maximum sorted section size, if that makes sense. Bottom-up merge sort is different. In bottom-up merge sort, we merge all the smallest arrays together. Then we merge, we always proceed by merging the smallest possible unsorted subarrays. Make sense? So it's kind of comparable to the idea of a depth first search versus a breadth first search on the recursion tree. You guys know the difference between breadth first and depth first searches? Hopefully? Yes? No? No? Okay. Well, we'll get to it when we do trees, but very, very quickly, let's imagine you have a tree, and instead of representing recursive function calls, imagine there's data stored in the tree, right? How do you search the tree to see if you can find the thing you're looking for, assuming that it's not like a binary search tree or some other thing that helps you search, right? There are two main approaches, right? You either perform depth first search, where you always search to the maximum extent of a branch, then backtrack, right? Do I have some colored chalk here? No? Okay. So, depth first search. You search down, keep searching in this manner. You're always searching the maximum depth you can first. Like you search all left branches first or something like that. Whenever you have a node where you haven't searched both branches, you always pick one, go down that, and that's depth first search. Make sense? What's the other one called? Depth first search and breadth first search. So breadth first search, taking the same tree, you search them basically by level, right? So first you search this one, then this one, then this one, 4, 5, 6, 7. It requires more bookkeeping to do a breadth first search, but depending on the type of tree and the structure of the tree, breadth first search can be more efficient. Again, like it's an algorithm class, everything is situationally dependent, right? Question?
Is breadth first by level?
Yes, breadth first is by level. So, the analogy breaks down a little bit with bottom-up merge sort, but essentially we are merging by level rather than merging in sort of this drill down, bring it back up, drill down, bring it back up fashion, right? Bottom-up performs all of the ones, all of the two sorts, then all the 4 sorts, then all the 8 sorts. Make sense? Cool. So, yes. Passing through the array, merging as we go, doubling the size of the sorted arrays. Keep performing the pass and merging subarrays until you do a merge that encompasses the whole array. I'm just going to bring the top-down merge sort back on the slide so we can see the difference, right? See how here we merge 2 small arrays, then we make a big one, then we merge 2 small ones, then we make a big one, then we make a bigger one, right? You guys are, am I hammering this too hard? You guys get the point? Okay. So, let's see here. Good. So, let's examine some minimum and maximum cases with respect to bottom-up and top-down merge sort. So, minimum number of top-down comparisons. Proposition, top-down merge sort uses between half n log n and n log n comparisons. So we might say then that this is not just a big O n log n algorithm, it is a big theta n log n algorithm, right? So the question kind of becomes, what is the smallest number of comparisons that merge sort needs to make in the merge step, right? I'm just going to do a small one here, right? So I'll just show you what the ideal case is, right? So this is the ideal merger, right? Because if we remember our merge sort algorithm, we're examining these. There we go. There we go. There we go. Now we've run out of that array, so we just pop the rest on here, right? If the arrays are already sorted, you only have to examine half of them. As a matter of fact, as is going to be briefly mentioned in a few slides, you don't even have to examine them, because if you know the position of this guy and these are adjacent, you know the position of this guy, and if this guy is less than this guy, then they can just be clicked together like that. But for the sake of the slides, assuming we don't use that clever trick, the number of examinations we need to perform is the size of the subarray we're merging divided by 2, right? So, if one subarray contains all the smallest elements, we only need to walk that array before appending the other. If you sort a sorted array, this would be the case at every level, right? So if you're performing merge sort on an array which is already sorted, then this is always going to be the case. Solving the above recursion yields C, with C equaling 1/2, yields C at n is equal to half n log n. Right? Make sense? Good, because at each level, we're going to get half n instead of a whole n. So that's going to carry forward. So that constant term, which we usually ignore in big O, is going to be 1/2, right? You know, plus, you know, multiplied by whatever the runtime constant is, right? Again, normally we ignore this, but, you know, we're trying to demonstrate the big theta, and in so doing, demonstrate the big omega. So, top down. Similarly, the maximum number of comparisons is made when both subarrays must be fully examined. So, all it would take is, you know, this guy being equal to 6 and this guy being equal to 5, and suddenly you have your worst case scenario, right? Because you have to go 1, 2, 3, 4, 5, 6. Full examination, right? So, if the input is an array is of size n, then at most n comparisons need to be made. If the above happens at each level of recursion, the total number of comparisons at each level is at most n. By solving the same recurrence equation with c equaling 1, we get c at n is equal to n log n. So, our proposition has been shown. Any questions? Okie dokie. So so we talked about comparisons. Now let's talk about array accesses. Reading memory from RAM is a reasonably in-depth and involved sort of thing at the level of the CPU itself. You know, in order to actually read from RAM, you require a load operation and a store operation in order to sort of pick it up and put it back. It's, you know, it's like, it takes like 3 times the amount of time to do that than it does to operate on stuff stored in register memory in the CPU. So it's, you know, you might be interested in the number of array accesses you have to perform, right? So, proposition. Top-down merge sort uses at most 6n log n array accesses to sort the array of length n. So, each merge uses at most 6n array accesses. So 2n to copy the subarrays initially, and we're talking about our specific Java implementation here. Remember, if we remember about our Java implementation, there we go. Our first step was to write the things we're sorting into an auxiliary array, right? Our next step is to put them all back in order, right? So, there we go. So we got 2n to copy the subarrays initially, 2n to put the values back in order, and at most n comparisons, each accessing 2 array elements. Make sense? So, hence the total number of array accesses after solving the recurrence is at most 6 n log n. So, now let's consider bottom up. The short version is that bottom up is basically exactly the same as top down in terms of these characteristics. It makes like 0 difference. So, proposition. Bottom up merge sort uses between the same amount of comparisons and the same amount of accesses to sort an array. So I guess you could consider this like proving equivalence of top-down and bottom-up merge sorts. So, the number of passes through the array is precisely log n. For each pass, the same argument made as in the case of top-down merge sort applies. The number of array accesses is exactly 6n, and the number of comparisons is at most n and no less than n by 2. Therefore, bottom-up merge sort uses half n log n and n log n compares. and at most 6 n log n array accesses to sort an array of length n. You may notice I'm going through this pretty quickly, and it's because I want to get onto quicksort. So, practicality. Number 2, 2 small improvements which can improve your runtime. Number 1, merge sort's not really useful. It doesn't considerably outperform insertion sort on very small arrays because of the overhead involved in all the function calls. So, if your array is less than 10 elements, you should just proceed by insertion sort, right? Obviously, you know, my set of dies, I have 12 of these, and it's still useful for, you know, if I had applied that with you guys, just split it and then insertion sorted it, then that wouldn't have been a very good demo. But, you know, it is what it is, I suppose. Number 2, I already mentioned this, but you can quickly check if 2 arrays are already sorted using a at mid is less than or equal to a at mid plus 1, so nothing more needs to be done. Stop if already sorted, that is, do not call the merge if the subarrays are sorted. This can be done by a simple and quick check. Obviously, if the arrays are already sorted, then you don't need to recurse on the subarrays either, right? So you save a considerable amount of time for checking for sortedness. And what's our usual check for sort? Well, I mean, you would have to drill down anyways to maintain the sortedness property. So scratch that last thing I said. That's wrong. So lower bound for sorting decision tree. Recall that there are n factorial permutations of n elements. You all know what a permutation is, I hope? Yes? No? Okay. The comparison decisions which result in these permutations can be represented as a decision tree. So if we have, in this case, 3 elements that we're trying to determine the sortedness of, imagine that these are like variables representing values, right? Excuse me. The code between comparisons, i.e. the sequence of exchanges, might be something like these. The height of the tree is the worst case number of comparisons you have to perform. You notice that not every decision, not every one of these results in, you know, this is not a full tree, right? Each leaf corresponds to one and only one ordering, at least one leaf for each possible ordering, right? So these leaves are not guaranteed to be unique either. So, proposition. In particular, these leaves are not guaranteed to be unique if the actual values of A, B, or C are equal, right? So, proposition. Any comparison-based sorting algorithm must use at least n log n comparisons, that is, the timing function is big omega n log n. We're not going to go through the full proof, but here's the proof sketch. We assume that the array consists of n distinct values, a1 through an. Worst case is dictated by the height of the decision tree. Binary trees of height h have at most 2 to the h leaves. Therefore, n factorial different orderings means, and n factorial different orderings means at least n factorial leaves, right? 2 to the power of h is greater than n factorial, ergo, h is greater than or equal to the log, the base 2 logarithm of n factorial. If we apply Stirling's approximation, I have included a link here, log of n factorial is approximately equal to n log n. You don't have to worry about not knowing. How many of you have heard of Stirling's approximation? Like, oh, that's awesome. But like, don't worry about it. I was hearing about it for the first time too. You're probably in a math program or something, right?
Physics.
Physics? Yeah, there we go. So, if you want to read up on Stirling's approximation, this is the Wikipedia link. Hence, h is greater than or equal to n log n. Therefore, any compare-based sorting algorithms must use at least n log n comparisons in the worst case scenario. Make sense? So, although these divide and conquer algorithms are very, very good and effective and wonderful, there is a physical hard limit to how good they can be. They cannot sort, they cannot perform sorting in linear time, for instance. Not possible. Mathematically impossible. Make sense? Any questions? Good. All right. So, let's move on then to quicksort. Quicksort is a very important algorithm. It is broadly considered to be one of the best sorting algorithms that yet exists. It has very good general performance. You may use shell sort if you're in a memory restricted environment. You might use other sorts depending on, situations. But quicksort is an excellent sorting algorithm to select for general purposes. Make sense? Good. All right. So here's the general idea. Oh, also, it was rated one of the top 10 algorithms of the 20th century. And given how many algorithms were developed in the 20th century, that's quite an impressive feat. So, here's how quicksort proceeds. Number one, in order to get some runtime guarantees, it's necessary to shuffle the elements prior to sorting. And I know that kind of sounds strange, but shuffling the array prior to sorting basically eliminates your worst case runtime where all of your, quicksort doesn't perform well on an already sorted array. So shuffling it ahead of time sort of guarantees that your higher and lower partition are going to be roughly equal, right? So that's why we perform the shuffling. So, step number one, select one element as the pivot, usually the head of the array. Step number two, create two subarrays from remaining elements via in-place swapping. So we are creating two partitions, one containing all of the elements which are not greater than the pivot, and one subarray containing all of the elements which are not less than. So it doesn't really matter whether the equal to case is in the top or the bottom half. You can sort of make that implementation dependent. It doesn't really matter. Make sense? So we recurse on both of these subarrays and then profit. So right. So before I demonstrate this for you, we do need to talk about the partitioning algorithm because it's a little bit strange. But this is the idea in general without getting into the partitioning, right? So we take, some set of characters or numbers, we scramble it, select the first element as the pivot, then we prepend it with all of those elements not greater than this element, and append all of those elements not less than. Make sense? Pardon me. We then recurse on these two subarrays, which may be of unequal size. Make sense? Okay. So, if you were to view an entire trace of that, it would look like this, but I'm going to do a demo, so I'll just jump over that and talk about the partitioning. So, the partitioning algorithm is a little bit interesting. It's essentially, you set up two scans proceeding from the extremities of the array towards the middle, right? To scan just means you go through them in sequence, right? Essentially, if you select a pivot, right? The numbers don't matter in this example. You scan this way until you hit a number that's greater than the pivot, then you stop. You scan this way until you hit a number that's less than the pivot, then you stop. And then you swap them, start scanning from this side again, looking for elements that are greater than the pivot, right? Once you hit one, you scan from the other until you find one that's less, and then you swap. Make sense? So, first we select the item that we are partitioning on. We'll call it V. Well, it's V in here. For some reason they call V the pivot. We then set up the left and right scan. Scan from the right until we hit a value greater than V. Scan from the left until we hit a value less than V. We swap these two values, then continue the scan. The two scans will eventually meet in the middle, and that's where we put V. The two partitions are guaranteed to be higher or lower than V, but not guaranteed to be sorted. So we must sort them recursively. So, this is a different approach from merge sort. Merge sort performs a very simple partitioning and then makes the combination part of the divide and conquer algorithm. It makes the recombination complicated. Merge sort makes the partitioning complicated and then the recombination very easy, right? By the time the array is fully partitioned, it is also fully sorted. Make sense? Okay. So we're gonna do the thing now. All right. So incidentally, before I get to the scan procedure, you might be tempted also, you can think maybe of a simpler way of doing this that doesn't require the scan procedure. You could, in theory, just keep two auxiliary arrays and then just pass through putting these elements in either a greater or a less than array and then just popping them on the end, right? It turns out that that's actually sufficiently less efficient that you might as well be performing merge sort. So the scanning algorithm is really where quicksort pulls ahead of merge sort. Make sense? Question?
When would you use the merge sort instead of quicksort? I want to assume never.
When you're learning how quicksort will work eventually, like in class, I don't know. I'm not sure what a use case is where you would want to use merge sort over quicksort. Merge sort uses more memory and takes more time and solves the problem in almost the same manner. So there's really, maybe someone will contradict me on this, but I'm not sure there's much argument for using merge sort over quicksort in any situation. There's probably some obscure situation in which it's better, but you know. All right, are we ready for quicksort? All right, so here we go. Step number 1, select the pivot. I'm going to be merging, I'm going to be sorting the equal to in the lesser half for this one, okay? So, we pick the pivot. I'll just put it right there, all right? So, we start our scan. Start our scan over here. This is greater than that, so we stop that scan here, this is less, exchange. Scan this way, this is greater, that's less, exchange. Greater than, less than, or equal to, exchange. Scanning. Boy, I'm performing a lot of exchanges here. Scanning, scanning. There we see. We skipped this one because it's still greater than, right? So there we go. Scan, exchange. Right? Scanning. Here we go. That's greater than. We have met. Right? Now we recurse. Although this is already sorted, I'm going to do it anyway. Well, actually it isn't. Well, it is, but you know. Pivot. Right? So that's the pivot. This is good. That's greater than. That's not. All right? So place it in the middle. That's now sorted. Well, this we'd have to sort because it's more than one. So, you know, trivial. I'm just going to leave it. Time. So, select the pivot. Scanning. This is greater. This is still greater. Greater, 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 greater. Ah. So there we go. Pivot. This is greater, less than, less than, less than, less than, less than. So, I got too many 4s. I didn't have a good roll. But, and then, simple recombination, and that's sorted. We didn't get any 6s? Jeez. Gonna have to use an inspiration point to re-roll that one. Anyway, let me just see if we've got. Okay, just one thing before we go. All right. I just want to point out that the way that they've written this down is a little bit like arcane because they're trying to fit everything on one line. You know, they're packing a lot into these lines with the while loops, right? So, like while, you know, while A is less, like the right scan is less than B, then, you know, like we've got a while loop, an if statement, and a break statement all packed into there, including pluses, which of course, as we know, are post-fix increment operators. So, like, it takes a little bit of mental energy to decompose these, but, you know, that is what it's doing. Any questions? All right. Thank you very much, folks.